Hey everyone, welcome back to Calculus 1. This is going to be lecture 5. In this lecture we're going to talk about infinite limits. Okay, so we've been looking at limits. We've talked about what a limit is. We've talked about how to identify limits analytically. We did a ton of examples in the previous lectures. In this one, we're going to move into a concept, the concept of infinite limits. So it's a slightly different idea, but very similar, very similar. Okay, so this will be section 1.5, entitled Infinite Limits. Okay, so previously we talked about how limits have to. One of the properties of a limit is that a limit has to be a real number, and so we want to contrast the idea of a limit with the idea of an infinite limit. So just keep in mind that what we define here in a minute or two is not a limit per se. It's like a limit, but it's technically something different, because obviously limits that have infinite value are not real numbers. But let's start with like a motivating example here. Let's consider the function f of x equals 3 over x minus 2. So obviously we can see this is a rational function, and it's going to have a problem in the denominator as x approaches 2. So the denominator goes to 0 as x goes to 2, right? So clearly. And so obviously the function is undefined at x equals 2. Right, so that we know. Let's plot it and just see what this thing looks like. I took a second and did that ahead of the class. And so let's say this is x equals 1, this is x equals 2. So what we're going to see is there's going to be asymptotic behavior of the function at x equals 2. And we talked about we talked briefly about the idea of an asymptote. Asymptotes are where basically the function heads off to positive or negative infinity, or maybe a better way to say it is the function increases or decreases without bound at the asymptote. So f increases without bound as x approaches 2 from the right hand side, and f decreases without bound as x approaches 2 from the negative side, from the left-hand side. All right, so obviously if you're heading this direction towards 2, then the function is shooting off to positive infinity. And if you're heading towards 2 from the other side, the function is shooting off towards negative infinity. Right, so you can kind of think of it as negative infinity down here, positive infinity is up there, right? And so what we do is what we're able to do here, what the kind of the point of this section is that we can denote this behavior using the limit notation. And so what we'll write here is that the limit as x approaches 2 from the right hand side of 3 over x minus 2, we say that limit is equal to infinity. And the limit as x approaches 2 from the negative, from the right-hand side, the left-hand side, is negative infinity. Right, so these are infinite limits. Okay, so these are a different beast than the normal limit. They have a different definition altogether. If you recall, with the normal limits, the real valued limits, one of the conditions is that the value L has to be a real number if the limit as x approaches c of f of x equals L. Right, so that's a real valued limit. right? So this is something kind of different, right? Because obviously this and this are not real numbers. Okay, so let's go ahead and let's just for the sake of underscoring the difference between the difference between a real valued limit and an infinite limit, let's remember the definition of a real valued limit. So roughly what we would have said previously is that if for all epsilon greater than 0, there exists a delta greater than 0, such that whenever 0 is less than x minus c, which is less than delta, f of x minus L was less than epsilon. Then the limit as x approaches c of f of x is equal to L, right? So that was roughly the definition. So we said, look, if you give me an arbitrarily small epsilon, I'm going to always be able to find a delta that's a positive value delta, such that if x is within delta of the limit point c, then the value of the function is within epsilon of the limit L. Okay, now obviously this would necessitate, this kind of a definition necessitates that L be a real number. Now, you can't talk about the distance between the value of the function and infinity, for example. That's a ludicrous idea, right? So here's where the definition would totally break down if we tried to apply it to functions where the conjectured limit was infinity or negative infinity. So let's talk about what the definition of an infinite limit is then. Okay, so another definition. So let's go ahead and this will be a little bit long-winded. I just want to make sure it's clear. We won't be using the definition. We're just going to kind of write it out to make sure that we've been exposed to it. So def, let f be a function that is defined at every real number in some open interval containing C. Okay. And then we'll say, of course, except possibly at C itself. Okay, that's kind of like the standard disclaimer there. So we'll start with f being a function defined at every real number in some open interval containing C. C is going to be the limit point. Then what we would say is that the limit as x approaches c of f of x is equal to infinity. What that means that for each m greater than 0, there exists a delta greater than 0 such that f of x is greater than m whenever 0 is less than x minus c, which is less than delta. Okay, so we'll toss in the negative limit in a second here, but let's just talk this through. So the limit as x approaches c of a function f is equal to infinity. What that means is that for any m greater than 0, now here the m is large. Okay, you would want to say make m as large as you can conceive, right? So if I give you an insanely large m, then what you need to do is go find a delta such that the value of the function is greater than m whenever I'm within delta of the limit point. Okay, so remember what's happening here. Let me just draw a little sketch here. All right, so I've got, let's say here's my limit point c, and basically the function is asymptotic at c. Let's say it comes over here and it kind of shoots up really high, right? Heads off to infinity. It increases without bound is what we should say. So if I give you a really large m, maybe we'll say this is a really large m up here, then I need you to find me a value of x such that the function is larger than m when I evaluate it at that x, right? And so what that's going to mean is that I need to find some delta that's really small, and hence is going to create a number x that is very, very close to c, right? So basically what it boils down to is that as I get infinitely close to c, then the value of the function has to get infinitely large. And so that's the idea with the infinite limit, and specifically the limit at infinity. Now, similarly, but kind of like flipped, is the idea of the function at negative, having a limit at negative infinity. So if we say the limit as x approaches c of f of x equals negative infinity, well, what that means is, so it means that for each n less than 0, there exists a delta less than 0 such that f of x less than n whenever 0 is less than x minus c, which is less than delta. Oh, this should be delta greater than 0. Sorry about that. Okay, and so this would be the similar idea, right? Like if here's my xy axis, and I've got an asymptote here, right, and the function is heading down to negative infinity, then as I get closer and closer to c, the value of the function is going to get increasingly negative, hence smaller than 0, right? So if you give me some arbitrarily large negative number, something way down here, then I'm going to have to get very, very close to c in order to produce the value of the function that is less than the n you gave me. Okay, so it's basically the exact same thing. It's just kind of flipped over. Here you want, up above, you wanted an arbitrarily large m. Here you want an arbitrarily small n, right? So it's kind of the same idea. Okay. Very good. So that is, again, the definition of the infinite limit, or the limit at infinity. Now, and again, contrast that with the definition of a regular real valued limit, and obviously you can see that there's a big difference, right? Here we're looking for a value of the function very, very close to a real number. Here we're looking for the value of the function that is beyond a large number m that is arbitrarily given, or beyond a infinitely small n that is in the negative direction, right? So that's the idea of the limit at infinity. So let's take a look at some examples and kind of try to get comfortable with these things. So let's consider the function f of x equals 1 over x minus 1. So we know that this function has a vertical asymptote at x equals 1, right? We just know that because we can look at it. So say that's 1. We know we've got some kind of a vertical asymptotic behavior here. What we don't know is, does it go up here? Does it go down here? What happens, right? So we don't really know. And so how do we figure that out? Well, to see whether and where the function goes, you're going to have to test some values. Okay, so we'll have to test some values. So let's go ahead and let x equals 0 be one of the values we test, and then the other, let's let it be x equals 2. So if we test x equals 0, then of course 1 over 0 minus 1 is negative 1. Right, now if we wanted to, we could plug in x equals 1/2 just to confirm, and we would get 1 over 1/2 minus 1, which would be 1 over negative 1/2, which would be what? negative 2, right? So these are obviously becoming increasingly negative. And let's test on the other side. If we test on the other side, let's go ahead and let x equal 2. And we would get 1 over 2 minus 1 is 1. Right, so that would be this guy. Let's test 1.5. And we would get 1 over 3 halves minus 1, which would be 1 over a half, which is 2. Okay, so we can see that these are increasingly positive. And so what ends up happening is the function basically is heading up from that direction, and it's heading down from that direction. Okay, so what we could say is that the limit as x approaches 2 from the left-hand side of 1 over x minus 1 is equal to, right, so that's approaching from the left, would be negative infinity. And the limit as x approaches 2 from the other side, from the right-hand side, is going to be, again, remember that's over here, and so we're heading this direction towards 2, the limit point 2, and as we do that, the value of the function shoots off to positive infinity. Okay, so there we go. So there are the two infinite limits for this function f of x equals 1 over x minus 1 at the value of x equals 2. Okay, another example similar to this. Let's take a look at f of x equals 1 over x minus 1 quantity squared. So obviously here we've got the function is undefined at x equals 1. Okay, we can see that it's got a denominator problem there, and so we're gonna assume there's some kind of vertical asymptote there. Okay, so again, here's your x equals 1. All right, so what is the function doing as x approaches 1? We assume it's heading off to positive or negative infinity. Let's just check. So let's test x equals 2. So when we do that, we get 1 over 2 minus 1 squared, which would be equal to 1. And let's test x equals 0. And we get 1 over 0 minus 1 squared, which is what? Positive 1 as well. Right, and so, and we could test closer just to make sure that we're seeing that there is in fact a trend up or down. Okay, and so when we do that, what we would confirm is that both sides are heading to positive infinity as x approaches 0, as x approaches positive 1. So in this case, we would say that the left hand and the right hand agree. Okay, so the left and right hand limits agree. So that means that the overall limit is, in this case, positive infinity. Okay, so from both sides, the function increases without bounds. So that, that means that we have an overall limit. Okay, very good. And so even though we've been kind of using this term, let's go ahead and formally define what we mean by a vertical asymptote. So if f of x approaches plus or minus infinity as x approaches c, then the line x equals c is a vertical asymptote of the graph of f. Okay. So, yeah, I mean, kind of, we've already, as I said, we've been using this terminology, but here's kind of more or less formally the definition. So in order for something to be a vertical asymptote, then the function has to approach plus or minus infinity as x approaches c. And if that's the case, then the line x equals c, the vertical line, is called a vertical asymptote of the function. All right, so that's all very well and good, all clear. Let's see. Let's have a nice theorem to go with this. So let's let f and g be continuous on an open interval containing c. On an open interval containing c. Okay. Now, if f of c is non-zero, okay, and g of c is 0, and there exists an open interval containing c, okay, open interval containing c, such that g of x not equal to c for all x in c, for all x not equal to c, sorry. Hold on. X not equal to c. In the interval, of course. Then the graph of the function h of x equals f of x over g of x has a vertical asymptote at c. Okay, so let's talk this through. So this is a kind of a wordy one. So let f and g be continuous on an open interval containing c. All right, so all that's saying is that you've got x equals c, it's some number on the x-axis, and you got two functions, f and g, both of which are continuous around c. Okay. Now, if f of c is non-zero and g of c is equal to 0, so these are f and g evaluated specifically at the value c. So if f of c is a non-zero value and g of c is equal to 0, and there exists an open interval containing c such that the value of g at c not equal to c for all x and not equal to c in the interval, then the graph of the function h of x, the ratio of the two, has a vertical asymptote at c. Okay, so this is basically a nice theorem for cleanup on rational functions. So basically what this gives us is the criteria for a rational function having a asymptote at wherever the denominator is undefined. Okay, and we'll see some really good examples of this at work here in a moment, but hopefully this is clear, right? If f and g are continuous on an open interval containing c, if the numerator is non-zero but the denominator is equal to 0, and there must exist an open interval containing c such that g of x is not equal to c for all x not equal to c. Okay, so that's an important piece of it. If all of that is met, then the function h has a vertical asymptote at c. Okay, let's see an example of this kind of at work and see what this looks like. So consider this guy. F of x equals 1 over 2 times x plus 1. Okay, where obviously x equal to -1, it makes a 0. Okay. Right, now otherwise this function is defined everywhere around c, right? We can put any value we want into this function for x. We just can't plug in -1. Everything else is fair game. Obviously the numerator is non-zero when x is equal to 0. It's just It's always equal to 1. It's just that denominator that becomes 0 as x as x becomes 1, as x tends to 1. And so this basically is all the criteria for the previous theorem, and so the implication here is that f has a vertical asymptote at x equals -1. Right, so this is your value of c here. Right, the numerator is non-zero as at x equals -1. The denominator is 0 at x equals -1. Everything around x equals -1 is well defined, no problem. It's just that one value, and so this is going to produce an asymptote. Okay. Another example. This one is slightly more interesting, I think. So f of x equals x squared plus 1 over x squared minus 1. So this is a nice function. Now we can do something here. Let's notice that denominator. We can factor that apart, can't we? Right. So we could say f of x is equal to x squared plus 1 over x minus 1 times x plus 1. Right. So that's this piece here can be broken apart into x minus 1, x plus 1. And so technically this function actually has two values of x where the denominator is 0. Right? So specifically at x equals 1 and x equals -1. Now, what happens to the numerator at these values? Well, in both cases, we're fine, right? So if you plug in 1, you square 1, you get 1. 1 plus 1 is 2. So the value is 2 at here. F of x is 2 when x equals 1. The numerator is 2 when x equals 1. And if we plug in -1 for x into this numerator, we again see it's also 2 there. So the numerator is non-zero. The denominator is 0 at these two values. Okay, so this function should have two vertical asymptotes. Okay, and in fact, if you plot it, here's what it looks like. Right, so you've got your +1 and your -1 here, and you do have vertical asymptotes there. Okay, so I'll just put 1 and -1 just so we know. Okay. And so you could test values on either side of this range if you wanted to. You could test, something close to -1, but this side of it, and something close to +1, but this side of it. And what you'd end up with is you'd see that it looks like this. So as we approach 1 from the right, we shoot up to infinity. As we approach -1 from the left, we also shoot up to infinity. What happens in the middle? Well, in the middle it looks like this. So the function has kind of these 3 regions where it has different behavior. Okay. And yeah, again, you could test this. You could starting over here, you could plug in x equals -2, for example, and you'd get -2 squared plus 1 over -2 squared minus 1, and so that'd be like 4 plus 1 over 4 minus 1, and you get 5 over, 4 minus 1 is 3, 5/3, so you get a positive value. Right, and so it's heading to infinity. You could test something closer if you wanted to confirm the trend. But then if you plugged in like -0.9, so what you could do is you could test x equals -0.9. Here you could test x equals 0.9. Here you could test x equals like 2, or if you wanted to get closer, you could say x equals 1.1. right? So it's always kind of a trade-off between, do I want to test a nice whole number, do I want to get really close and see what's happening? And then over here you could test like we did here, x equals -2. So we're testing here. Let me make sure I'm clear on that, just to determine the directionality of the increase or decrease. Or, you know, you could test x equals -0.9 or something like that. -1.1, sorry. Okay. So you could test around the asymptotes to see what direction things are headed. Okay. And what you derive is, you know, a nice visual like this, something like that. Okay. Another example. It's important to do lots of examples in Calculus 1 because this material is new, right? These are new ideas, things you haven't seen elsewhere. And you may not remember, but the way you got good at algebra was solving lots of equations, plotting lots of functions. The way you get good at calculus is looking at lots of examples similarly. Let's take a look at this one. This one's a little bit trickier. This is f of x equals x squared plus 2x minus 8 divided by x squared minus 4. Okay, so this one is going to be a little bit different. Now, when you see these rational functions and you got polynomial in the numerator, polynomial in the denominator, you better check to make sure you can't factor these things, because if you can factor them, then the story would potentially change a lot. Because if you just look at this at face value, you might say, well, 2 or -2 is going to make the denominator 0, so you know, no worries, solved. But actually, this thing can be factored. Right, so the denominator can be factored into, this is a +2 -2, right? So x plus 2, x minus 2, right? That's what that's all about there. And you might be inclined to say, oh yeah, okay, fine, no problem. Yep, so this is 0. But now, to really strictly and thoroughly apply the previous theorem that we saw, we have to make sure that the numerator isn't 0 at -2 or +2, right? The denominator certainly is. We have to make sure the numerator isn't as well. And another way to say that is we have to factor the numerator if we can, right? And in this case, you can. This factors down nicely into x plus 4, x minus 2. And then, of course, on the bottom, you've got x plus 2, x minus 2. Now, what ends up happening here essentially is when I test the denominator at x equals 2, then the denominator is 0 specifically because of this factor, right? X minus 2. If I plug in a +2, I get a 0. 0 times this makes the whole thing 0. Now, it's also the case that if I were to take x equals 2 and plug it into the numerator, I would notice that the numerator is also equal to 0 at 2. Right, and that is because the numerator can be factored down like this. It has a root at 2. Okay, so this polynomial x squared plus 2x minus 8 has a root at 2. Now, you can see it when you do the factoring, and you can kind of think of it as like, oh yeah, those technically would cancel out, and I would have x plus 4 over x plus 2. Now, this gives a different picture of the asymptotic behavior and non-asymptotic behavior at the two values x equals 2 and x equals -2. So at x equals 2, the denom is equal to 0, and the numerator is equal to 0. So that implies not equal to 0, sorry, at x equals, sorry, I want to start with -2, my apologies. At x equals -2, the denominator is 0, and the numerator is non-zero, right? So that's going to imply an asymptote. Okay. Contrast that with x equals 2, where you do indeed have the denominator equal to 0, and here the numerator is also equal to 0. So that implies that this is not going to have an asymptote at x equals 2. Okay, now the function is still undefined at x equals 2. Right, they both are. This one's undefined at x equals 2. It's also undefined at x equals -2. But you have an asymptote at x equals -2, whereas you just have a hole at x equals 2. Okay, and then you can kind of see, well, hopefully you can see clearly, actually, that if you unwind this numerator, in fact, it factors, and this function f is equivalent to this other function, x plus 4 over x plus 2, except at the one value of x equals 2. Right, and so that was another theorem that we came across earlier on, and we're able to see that kind of come back into play. So what does this function actually look like? Well, let me draw it. So the function, again, just to write it, is f of x equals x squared plus 2x minus 8 over x squared minus 4. Right, and the function kind of looks like this. So here's, we'll say, x equals -2, and there we have a vertical asymptote, and the function kind of heads down like that as we approach it. Now over here, the function looks like this, but we just have a hole. Nice smooth behavior otherwise over here at +2. So this would be 1, 2, -1, -2. Right, and so you can see that over here you've got the asymptotic behavior. But because that numerator also is 0 here, you don't have an asymptote, you just have a hole. Okay. Yeah, and so this would be an example of a removable discontinuity here, and this would be a non-removable discontinuity there. And so the two different types there on one graph is nice. Another example. Examples are king. Let's consider f of x equals x squared minus 3x over x minus 1. And so here we can see that f is going to have a vertical asymptote at x equals 1. Right, we can obviously see that the denominator is 0 at x equals 1. What happens to the numerator? Well, it's 1 squared minus 3, which is 1 minus 3, which would be -2. So denom equals 0 at x equals 1. The numerator is not equal to 0 at x equals 1. So undefined at x equals 1 naturally, and asymptotic at x equals 1. And so this one looks real similar to one that we previously saw. We could test values. Oops, sorry, it's on the wrong side. Let's take this as the y-axis, and this is the x-axis, and here's our x equals 1. So this one is going to look something like this. Again, we can test those values, right, to determine the behavior. We could test 2 and we could test 3. At x equals 2, you would get 2 squared minus 3 times 2 over 2 minus 1, which is like 4 minus 6 on tops and then a 1 on the bottom, so it'd be -2. Right, so as we approach, so over here it's heading negative, and we could test closer. We could test like x equals 3. And so that would be like 3 squared minus 3 times 3 over 3 minus 1, which would actually give us 9 minus 9 on top, so this would be a 0. And so obviously this is, as we get closer to 1, this is going to -infinity. And we could do the same thing on the other side. So we could test x equals 0. And we get 0 squared minus 3 times 0 over 0 minus 1. So that's a whole bunch of zeros. And we could test x equals -1. And then we get negative 1 squared minus 3 times negative 1 over negative 1 minus 1. Okay, run through all of that, you'd get 1 plus 3, so you'd end up with a negative 2 altogether here. Okay, so just to summarize, here's x equals 1, right? So when we're at 3, it's up here at 0. When we get to 2, it's down here at negative 2, so you can see the direction, right, is heading down. Similarly, with this one, when x is negative 1, over here, we get a value of negative 2. When x moves to 0, we get a value of 0, right? So you can see that this one's heading up, this one is heading down, right? And so this is approaching positive infinity. And so take these things together, we can see that there's no overall limit, right? But we can see that the limit as x approaches 1 from the left of x squared minus 3x over x minus 1 is equal to positive infinity, and the limit as x approaches 1 from the right of x squared minus 3x over x minus 1 is negative infinity, right, coming down. Okay, and so those two facts together would tell you that the overall limit doesn't exist. There is no overall infinite limit, right? So the limit as x approaches 1 of the function does not exist. And that's just because the left and the right hand limits don't agree, right? Just to be clear, just to be explicit, because the limit as x approaches 1 from the left of x squared minus 3x over x minus 1 does not equal the limit as x approaches 1 from the right of the same function. Okay, so the two left and right hand limits don't agree, the overall limit doesn't exist. All right, very good. So yeah, that's the last example. I do want to end with a nice theorem that can be used if you're following along with homework in this course. This is very convenient. Theorems are usually convenient. They're usually meant to be helpful. What's the point otherwise, right? So let C and L be real numbers. And let F and G be functions. Such that the limit as x approaches C of f of x equals infinity, and the limit as x approaches C of g of x equals L. Then, all right, so here, before we get into the what's the point, the punchline here, keep in mind here you're dealing with a real valued limit here, and you're dealing with an infinite limit here, and so this theorem will kind of give you the interplay of the two, right? Kind of tells you sort of like what happens when you combine them. So there's a couple of things that we explore here. So the limit as x approaches C. Now notice they're both approaching C. Okay, so the limit as x approaches C of the sum or difference. So what happens? Can we imagine what would happen? Right, this piece of f of x plus or minus g of x, this piece is going to infinity. This piece is going to a real number. What's going to happen overall? Hopefully it's clear that the whole thing heads to infinity, right? Whole thing increases without bound. This thing increases to a limit value L. This one heads up, increases without bound, so overall the whole thing increases without bound. What happens with the product? The product of f and g? Well, same deal, right? That's, if the value here goes to infinity and this one goes to a real number L, then the product is obviously going to be infinite. Now this is heads off to infinity only in the case where the limit is greater than 0. Right? Naturally, like if g is a negative number, g is heading towards a negative number, then the whole thing would do the opposite. In fact, that's bullet 3. So the product will be negative infinity if L is less than 0. Okay. And then the final thing here, limit as x approaches c of g of x over f of x. What happens there? So this g is approaching a, the limit here is a finite real number. The limit of f is infinity, positive infinity. So if I take a finite real number and I divide it by something like infinite, what happens? Well, you get a vanishingly small number in each group, right? So technically this will go to 0. Okay. So this is a nice theorem, kind of summarizes a lot of the interplay, and we'll come back to some additional ideas regarding infinite limits as we travel on further. We'll get into asymptotes that exist on a slant. We'll get to limits as x approaches infinity, right? We'll come back to some of these other ideas a little bit later. But for now, that's where that's what we'll stop with. We'll kind of get this the piece of the picture you have right now is all you need really to move into the next stage of calculus. And so with that, that's going to be the end of this section 1.5. And then next up is derivatives. Right, so this is one of 3 big topics that calculus introduces to mathematics. They introduce more than just 3, but you've got the limits idea, which is a new calculus idea. Next up is derivatives and differentiation, and so we'll get into that next time. But yeah, we will be revisiting limits. They all throughout Calc 1. So this has just been kind of the introductory information on limits. So we'll see you next time.